Now let's consider the relative acidities of protonated atoms. And one of the ways to do this is to look at the stability of the anion. And so to do that, let's look back at actually kind of a general chemistry type example. If we look at hydrofluoric acid, you'll recall that you were probably told that this is a weak acid. And then that hydrochloric was one of the strong acids. And so, that is stronger than HF. And part of the main reason for that is that the negative charge is just more stable on a chlorine. You might not have been told that hydrobromic acid is a bit stronger than hydrochloric and that hydroiodic acid is even stronger. But this, again, has to go with the stability of the anion. Now, you might be saying, but the fluorine is the more electronegative element here. So it's easier. It likes having electrons. It's probably easier for it to take an extra electron or to be charged. And, it is electronegative and it does help in that regard. But don't forget that chlorine is a lot bigger than fluorine. And bromine's a lot bigger than those, and iodine is the biggest. And so when you get an atom that's just that much larger, you will end up spreading out that negative charge over a larger area or volume. Spreading charges over a larger volume increases the stability of that anion. We've talked about that when we're talking about resonance, but the same is true when we're talking about just atoms. The larger the atom, the easier it is to take that negative charge. Now, let's go back to HF and talk about electronegativity, because it is more stable than things that are less electronegative. So if we were to deprotonate methane, then we would have this anion. And that's pretty unstable. And the pKa for methane is reflective of that. It's about 48. And so that's less stable than the nitrogen species. And the nitrogen is a little more electronegative, so it's easier to take that charge. And this is somewhere in the 37, 38. I didn't find an exact number on that one, but if you have some carbon groups on here, it's about 38. And so this is close. Hydroxide, pKa for water is 14. So we're getting more stable. And then fluorine is the most stable out of this group, 3.2 pKa. So out of this row, you'll notice that all of these are in that same 2p kind of row, the second row of the periodic table, and we're moving across, increasing in electronegativity. And as we increase in electronegativity, the negative charge gets more stable. Now, this is what we see for negative charges. What about if we have a positive charge? What if we evaluate from that direction? So here we have hydronium and we have ammonium. Now, the plus charge is less stable on the oxygen than it is on the nitrogen because oxygen is the more electronegative element. Since this is less stable, it should be more acidic. And since this is less stable, this will be more acidic. All right, back to this stability here for the anions. Larger atoms are just better at taking the charge. That holds true elsewhere on the chart, not just for the halogens. So if we compare carbon to silicon, and silicon is right below carbon on the chart. Same kind of species, right? A deprotonated version. This silicon species is more stable. And that, again, is because larger atoms are better able at handling the negative charge because they're able to spread it out more. Now, just to be clear, when I say acidities, I'm talking about, in this case, I'm talking about these particular species. But up here, I'm really comparing methane to ammonia to water to HF, right? So maybe I wasn't super clear on that. So we're just using the anion to illustrate how we can evaluate these, right? Because either the acid is less stable or the acidic form is less stable than the others, and we can compare those directly because these are the charged species and we can see that a lot easier. Or we're looking at the anions of the acid and we can see the stability there. And we're doing that because these species are neutral and these are charged, and it's a little easier to think about it in that way, right? And these are, again, we're comparing really water and ammonia. And this is a way to compare that kind of structure. So, larger atoms generally mean more stable anions. More electronegativity generally means a better stability in the anion. And if we have positive charges, that will be less stable on the more electronegative element, and so that will be greater acidity in that case. So, thank you for joining me for this video, and we'll see you on the next one.